Yeah, hi. I'm Martin. I work at Cross Labs here in Japan. And I want to thank the organizers for inviting me and giving me a chance to talk about this research on when we can see a Moore machine as an agent. So there will be a brief motivation and then kind of the vibes of our approach maybe, and then I'll give the definition of this Bayesian agent interpretation, which is the kind of formal or technical part. I'll make some comments and then summary. So one thing that would be nice to have, I think we will in the end agree, I hope, is a kind of general and formal characterization of when some open dynamical system, which is a system with inputs and outputs and some internal state, when such a system maintains or updates beliefs about a model of some other system, where this other system is the thing that causes the inputs to this open dynamical system. And additionally, when this system acts in order to achieve a goal in this modeled system. So this is kind of a very long-winded way to say when exactly this open dynamical system is an agent. Or, yeah, at least one kind of agent. So just to drive this home from another perspective, what we want is that whenever some open dynamical system is capable of somehow accumulating information about some modeled environment and actively pursuing some kind of goal in that modeled system, then this characterization should reveal that it's doing this. So my original interest in this question comes from my interest in formally understanding what living organisms are. So like Manuel said, I come also from A-Life, and this is like a fundamental question in A-Life. And I'm interested in this because I think life is actually very closely related to agency. But this is not what this conference is about. So, but I think you maybe have a similar interest in such a characterization, because if we had it, we would maybe be able to prove things like safety critical things about the beliefs and the knowledge of some system, and in particular the goals of this system. So what's our approach? I kind of call it vaguely a relational approach, and it kind of says, so this is very informal, but kind of a system is, or something is, even what it can be consistently interpreted as being. So if a system is some agent, then we say there must be some interpretation of that system as an agent which witnesses or reveals that it is an agent. And why do I call this relational? Because having an interpretation in terms of some model system or some goal, that's a relation to this model system or the goal. So that's why I call it relational. And why is this an advantage? I mean, I can't really prove this kind of statement, but it seems to me that like what being an agent is kind of like super mysterious. Okay, what does this mean? It is an agent. But if you have whether you have an interpretation as an agent, that's something I think we can kind of check, and it's like we can make this kind of formal characterization of this. Okay, so in our work we've up to now defined two kinds of interpretations. The first one, we call it a Bayesian reasoner interpretation, and this kind of says how when a system does some kind of Bayesian filtering on some hidden state of the model, of its model, of the causes of its inputs. And the second one is the one I'll talk about now, which is called the Bayesian agent interpretation. And this reveals when a system can be seen as solving a partially observable Markov decision problem. So it's actually, so that involves the goal, which is the maximization of the expected cumulative reward. Okay, so what is this thing? So first, let me say what a Moore machine is, because our definition only works for Moore machines. Moore machines are very general things, but this is what we make statements about. So a Moore machine has two functions. The first is called the machine update function. It takes an input and an internal state. So the internal states are called M here for machine states, and input is I. So it takes an input. It takes an input and a machine state and produces a new machine state. So in these kind of diagrams, the boxes are functions, and on the wires there's sets, and they go from left to right. The second part is the update function, output function, and this just takes an internal state and maps it to some output. Those two machines here, I'm going to assume they're deterministic. There will be some stochastic ones later. Okay, so next. What the Bayesian agent interpretation does informally is kind of you guess, or first you need to guess an interpretation, which consists of this POMDP and a interpretation or belief map. And then you check if the beliefs that this belief map associates to the internal state of the Moore machine update according to Bayes' rule. That's why it's called a Bayesian agent interpretation. And then you check if the outputs of the machine are equal to the optimal actions for solving the POMDP. So maybe one thing I want to say is that this Moore machine we call the it's not really an agent, it's just a machine. Like, you don't know yet if it's an agent. We have kind of separated it from, we have kind of solved the Markov blanket thing that Manuel was talking about. We have a separate thing in itself. It's a mathematical object, not necessarily something in physical space. So we make this assumption that we know that we have this mathematical thing, and then like it could be a program, a software program, and each of these functions could be neural networks. Okay, so now how does this POMDP guessing an interpretation work? So a POMDP is defined by some set H of hidden states. So those are kind of like the environment states, and a model. And this model is about what causes these inputs. And the model also is allowed to have a hidden state that is dynamical, so also produces new hidden states. So the model basically takes a current hidden state and an output of the Moore machine, and then gives you a next hidden state and the input. And since it can be stochastic, it actually gives you a probability distribution over the next hidden state and input. So stochastic, this blue bar here, that just means that it's stochastic. And we also have a reward function, and that takes a hidden state and an observation to some reward, and that's the cumulative expected reward is going to be the thing that's going to be maximized. And the other thing is this interpretation map, which is kind of the main, I mean, we didn't invent this. I mean, this exists in the literature, but this is like a very important part of our approach. And this associates to each internal state of the machine probability distribution over hidden states. So probability distributions over hidden states are also kind of called probabilistic beliefs. So this is our notion of beliefs. And then if you have guessed this kind of interpretation, then you can check if your machine actually has this interpretation or is consistent with this interpretation. And how do you do that? Well, you have to check this equation, which looks maybe a bit scary, but if you squint a bit and you know some Bayesian, Bayesian updating well, then you can recognize that this is actually Bayesian updating. And down here is the string diagram version, which maybe helps you a bit more, I don't know. But let me go through this really quickly. So maybe up here you see this is the new state mu of I and m. This is the new state of the machine after receiving input and starting in state m. Mu of I and m is the new state. And this kind of is the parameter of the interpretation function or the input to the interpretation map, which gives you a probability distribution over the next states. And this probability over distribution over next state has to be this Bayesian posterior thing. So you can also see here, m is the current is the internal state, and it has an associated belief over hidden states and also an output, and those are both fed into the model and then give you kind of a prediction of the next hidden state and input. And here, what this side shows is that if you predict the same input and get it and put it into this machine, then the new machine state, the belief associated to the new machine state after the update here is actually the same belief as is actually the same as the one you expected in a way. So this is kind of the way Bayesian updating works. And so you check this condition. This is all about having consistently updating beliefs. And the other condition you have to check is that your actions are actually optimal, or that the outputs of the machine are the optimal actions. So for this, you need to know the optimal actions for your POMDP, which is not easy at all, but let's assume you have them. And then you just check whether in each machine state, the output is the same as if you take this machine state, check what its belief distribution is, current belief about the hidden states is, and then check if under this belief the optimal action is the same as this output. Okay. So that was the tough part of the talk. And do you know how much time I have? No.
I think you have 3 or 4 minutes.
Okay. Fact. Okay. So the first thing to note about our definition is that it's independent of the environment completely. We only take the Moore machine and check if it has, and we guess these interpretations and we check if if the machine is consistent with them. And for this we don't have to put it into contact with the environment at all. This is a pure property of the machine, which means that if you put this machine in contact with some environment, it will have this goal that we found out before. But this goal might not even be achievable in this environment, might not even exist. And so it might completely fail to achieve its goal or to do anything sensible in this environment you put it in contact with. So we say an agent is not something that achieves something. We say an agent is something that tries to achieve something. This is kind of the main difference to what Matt's perspective, which I think is kind of complementary and not less important, because he kind of says an agent is about what it achieves, and we kind of say it's about what it tries to achieve. And yeah, I think there will be some future perspective, and that relates these two things. What else do I want to say? Every Moore machine has trivial interpretations, so there can be only a single hypothesis or a single hidden state, and a constant reward function, and then all policies are optimal. There's also an interpretation that kind of makes it so that whatever the machine is doing, it's optimal. But yeah, those are not the only interpretations, and actually one machine has multiple, like it has these two, and then it can have many more. And they probably, I don't know, they should be a probably some here, form a category. And we are investigating this. And the other important part is that it's only a sufficient condition for agency. So this exact Bayesian belief updating that we check with the consistency equation is actually too strong. It forces the machine to remember too much about the past, not only what it needs to remember in order to take the optimal action. So that's for the safety people, it's probably a bit disappointing. But we're working on doing this approximate version, which will hopefully allow us to have a necessary condition for a Moore machine to be an agent. Okay, there's also stochastic machines, but these ones are still pretty boring, the ones that are in this paper, because the interesting ones also need this approximation. So I think I have some more slides, but I think I'm going to stop here because it's just a kind of summary.
You have some more time if you'd like to.
Okay, let me just go through this quickly. So I described some steps towards formally characterizing when some open dynamical system maintains beliefs about a modeled system and acts in order to achieve a goal in this modeled system. And I think for the AI safety applications, we need a theory for arbitrary beliefs and belief updating mechanisms and arbitrary goals and problems. And we need the necessary and sufficient conditions for when a system pursues any of those goals. But we don't have this yet. We just have a sufficient condition for agents, and we only deal with probabilistic beliefs and exact Bayesian belief updating. For example, there's also things like possibilistic beliefs, and maybe there are many more kinds of beliefs. I wouldn't say that we are that we already know exactly how far these, like what really a belief is and what knowledge is. But that's all future research. Thank you. I'm happy to take any questions.
Do you have any questions from the audience? Should we start with Colin in the front at the middle? Runners? Colin right, front middle.
Thanks, Mark. This is an embarrassing question as a question after the talk. It's really a clarifying question. So how does a Moore machine differ from other standard machine representations, and why do you prefer the Moore representation? What does it allow you to do that
Yeah, so it's not a very strong condition, but okay, so why do we want this? So the important part about a Moore machine, there's one other famous kind of machine, which is called a Mealy machine. And actually, this is a Mealy machine. It produces kind of, so the inputs to the environment are basically the outputs of the environment. So this machine has one function, that turns the states and inputs to new states and outputs at once. The Moore machine has two functions. One that turns the input and the machine state to a new machine state, and one that produces the outputs. So why do we do this? Why do we like this better? Well, the main reason actually is, to be honest, that these Moore machines are the kind of things that solve POMDPs.
Okay.
I mean, it's a subtle question in some way. We could talk about it, but I would have to know what your background is.
I'm not quite old enough to know Alan Turing, but I understand what Turing machines are, and I know finite automata. And so that would be the natural model that I would be thinking in terms of. So
Right. I mean, Moore machines are also, like the finite Moore machines are also finite automata. So there's no... And there's also a theorem that you can turn any Moore machine into a Mealy machine. But the thing is that maybe one thing, the Moore machine kind of produces an output first, and then it gets an input and updates its state, and then it produces an output again. A Mealy machine is something that you cannot produce an output by itself. You always have to give it first an input. So the Mealy machine is kind of the thing that reacts, and the Moore machine is kind of the thing that can start some interaction process.
And a null input doesn't change that?
A null input?
Yes.
So you
Giving the Mealy machine a null input doesn't...
If you give the Mealy machine a null input, it must have, in its input set, it must have a null input to deal with. So you can specify some kind of additional, like you can specify some state as the null input, but you will still have to give it to it in order for it to do its thing. It's kind of, by definition, you have to give the Mealy machine an input for it to produce an output.
Okay.
And like, if you don't give it its arguments, you can't apply the function, no. So that's why it's kind of, it's like, but this is like the mathematical precision that, I mean, that's why mathematicians, like, let's say 5 years ago, I wouldn't have cared about this one bit, but it seems like maybe we have to.
Any other questions? Brandon, at the back in the middle.
Or maybe, like, for proofs. The thing is, in the end, for proofs, you have to care about these things. Like, you cannot prove things without making sure that everything is like the way you need it to be.
Thank you, thank you, Martin. Agent foundations is kind of close to my heart. I'm over here. You brought this up, but there's clearly trivial examples of your definition of agency here. Like a thermostat, you could model it as one of these machines,
Right.
but it doesn't fit the intuitive definition of an agent. And it seems like there's a broad class of things, like even autopilot on a 737 or something would fit, a model that might fit a model like this.
Why not? I mean, why does it not fit an intuitive notion of an agent?
I mean, we're not worrying about the safety of thermostats.
Right. That's true.
So,
but that doesn't mean that it's not an agent, no? I mean, well, at least in my opinion, it doesn't, because it's still trying to do something. Like, the thing it's going to try to achieve is perfectly fine. Like, it's not going to kill us unless it's trying to make the temperature 300 degrees in this room, then maybe.
Sure. Then your thermostat is broken. But I mean, sure. Like we can have a very extremely broad definition of agency, but if you're worried about some of the more intractable problems in safety or something, it seems like it draws a pretty broad class of things, and we'd want to separate out agents from dangerous agents or potentially dangerous or some other class of things.
Right. I think, yeah. But I mean, like, I think you could use stronger definitions of agent, and I think like Matt's definition is more like also going in this direction. And I think we need to to understand agency, we need to understand all of it. Like, we can't just say, I just want to. I mean, like, I think it's not a good. I mean, I don't know. My intuition would be. I mean, I'm also interested in it from the biology part, but my intuition would be like, if you only try to understand this one part of agency that's really, where you already know it's important for safety, maybe you're gonna not actually understand the concept of agency, and then you're not gonna be able to prove the things you want to prove. So if let's say, if there really is this category of interpretations, then in this category, there should be like specific goals and like specific interpretations that are maybe dangerous, and they should have a property of something should make them dangerous, and then we should just formally say what that property is. But we also, like, if you want to understand the dangerous agents, I think you also need to understand the non-dangerous agents to figure out what is the property that makes the dangerous ones dangerous. No? You need to, and hopefully formally. So, I mean, but this, I mean, I think you can have a different approach. I think it's fine. But like I'm kind of more envisioning this. You have this theory of agency, which is like general, and then like in this theory, you find this these specific parts that are relevant for safety, for example.
Okay, thank you. I mean, my intuition is that agency is not directly where the boundaries of the danger are or something more like this. I would care about what you brought up. Having a broken thermostat is a problem. And if we have a really intractable thermostat, we care about trying to fix that. So it's like, I think you're hitting on something interesting here, but it seems somewhat orthogonal to agency to me in a little bit.
I mean, yeah, I think there are people who use this word in maybe more like the way you mentioned. I think when people say agentic, I don't think that's really close to what I'm talking about, which also confuses me, but because I don't come from this background really. So, but I think, yeah, I think this, that's right, yeah.
All right, thank you very much.
Question from the live stream?
Yes, we've got a question from the live stream. Alisa asks, when you say that an agent tries to achieve its goals, what is a goal here? And I think I will add from myself. Does your conceptualization of agents as Moore machines allows you to offer some formal criteria for goals? Thank you.
Right, so here we use this, we use reward functions to formalize the maximization of expected cumulative discounted reward as goals, basically, so which are just given by, you choose a reward function and then you have a goal. And then there's this theorem about how all preferences can be represented by reward functions. So this is it's a very broad definition. I'm not really sure if that it really incorporates everything. But I think, yeah, so that's the idea. And so, yeah, maybe one more thing to say is that these goals, these reward functions, they are not, the way we formalize them, they don't have to be anywhere in the system. They exist as part of this interpretation, which is kind of a mathematical relation of the machine to this model system. So, or to the goal also. So yeah, like in some way, when this interpretation exists, maybe in some way it means that this goal is somewhere in the system, but this is the way it's in. The way it is inside the system is basically witnessed or revealed by the existence of this interpretation. So that's also the kind of categorical approach that basically things don't contain anything. Things are completely specified by their relations to everything else. And that's the kind of...
So it's more of a manipulation of relations rather than numbers.
Exactly, that's why I say relational. I could have said categorical, but it's much more scary term, so...
Thank you.
We have time for one more from Ryota in the white in the middle.
Oh, hi, Martin.
Hi, Ryota.
Yeah, I was wondering whether you can always find some map to interpret like any Moore machine as a Bayesian agent. It seems like you can always find something, and then maybe there's no correspondence with the actual environment, but it's always a model of something. So then, like as long as you can first find some sort of Moore machine in a dynamical system, it always has some sort of model. Or can you find an example where you cannot find this interpretation map?
I mean, there's some examples, but so the thing is that these two, they always exist, and the second one is not even completely trivial. Even though, so when there is a case, it's not very nice. So if the machine is stochastic and every state can transition to every state, for every input there's a probability for the state to go to every other state, then it only has a trivial Bayesian interpretation, and therefore it only has a trivial agent interpretation. But I think the correct perspective to take is that it's not a problem that everything is a kind of agent in some trivial sense, because the interesting things are the powerful interpretations, like the ones where, I don't know, the goal is really like some abstract thing, or the goal is kind of, I could say, a dangerous thing, you know, like, yeah, that's the idea. I mean, like, we don't really have very nice examples for this yet, and I think we need them, but that's kind of the intuition I have, that you need to look at all of them and the structure of them, because, I mean, yeah, hopefully they form a category, and there's like the most dangerous interpretation, or just the most, I don't know, the most compressed interpretation, maybe, with like the kind of final, most particular goal or something. I think that's the hope.
Okay. Yeah, thank you.
Okay. Thank you very much, Martin.
Thank you.